right, so on Monday, we introduced the course, and we talked about some of these big picture concepts, and we covered a lot of the stuff in this first big picture. We talked about how we obtain data, and it can come from a sample where we randomly sample, try to get a sample that is representative of the population. We also talked about conducting an experiment where we've done random assignment of the treatments, and if we do an experiment in that way, we might be able to draw a cause-effect conclusion from what we have, okay? We also said anecdotal evidence is kind of what we all experience in our lives, or just the other stories that we hear from other people. And while it's very real and whatnot, from a statistical standpoint, it's difficult for us to work with anecdotal evidence and draw any kind of conclusions there. All right, today's lecture, we're going to get into issues like displaying and describing data, and it's not one of the big points here. In terms of the big picture, now we're kind of delving into kind of some of the mechanics or some of the important topics that we need in order to develop some of the other points here, okay? So if I have to sum up the goal for today, it will be that you are able to describe a distribution, okay? Be able to describe a distribution of data. Okay. All right, and we'll say graphically and numerically. Okay. And this probably requires us to define what a distribution of data is in the first place, okay? All right, and so that's where we'll start, okay? So what is a distribution? Okay, the idea is that we're going out and we're collecting a certain aspect of information about many observations, okay? So for example, let's say this classroom represents the sample of people that I'm going to work with, and we are going to select some variable about you, maybe your age, okay? And we would go around and we would gather your data, okay, and we would organize it in a table. And so I don't know how many students are enrolled in my class, but let's say there's 130 of you enrolled in the class, okay? So if there's 130 of you in the class, my data table would have how many rows? 130, okay? You can shout that out, all right? So if there's 130 individuals, in our data table, each row represents an individual, and so that we're going to have 130 rows in our table, okay? And if I've collected only just one piece of information, your age, we would have one column, okay? Perhaps we would have a second column where we've got an identifier, either your student number, your name, or something to kind of distinguish one person from the other, but it really, actually, that column doesn't even matter. Just the column of ages is what matters, right? So let's just back up, and we'll just say here's our data table, and it's going to basically okay, so we've got 130 rows, and I've got one column. Okay. And the distribution, when we talk about the distribution of data, what we're talking about is saying what values appear in my data, which values are more common, which values are less common, okay? So the distribution is talking about basically how are the values, quote, distributed among the number line, right? So your number line technically goes from minus infinity to positive infinity, right? But obviously no one here is minus infinity years old, and no one's going to be positive infinity years old, or no one here is over 100 years old, or things like that, right? And we're just talking about the values that we have in our data set. How are they kind of distributed on the number line, right? Okay. All right, and so, based on your own perception, what do you think? What do you think the numbers we would see would be in our data set? What do you think would be a common value in our data set here? So we're dealing with this classroom right now. 20, okay, so we think a lot of people are around 20, okay. What other values might we see? 19, 21. All right, who thinks they are the youngest person in the classroom? I don't know. Anybody? How old are you? 17. Anybody beat 17 for the youngest? Okay, all right, you are indeed the youngest then, all right. So our distribution has a lower end of 17, okay? Who thinks, I don't know, this is maybe a little bit more sensitive, other than me, who's the oldest person in the classroom? Who do you think? And no one is willing to volunteer this. Okay, well, I have no idea who the oldest person in the classroom is, okay? The oldest number could be 26, could be 32, I don't know, all right? I'm not gonna force anybody to out themselves here. But probably, I suspect that your intuition is mostly correct in that we're going to have a bunch of 19 and 20-year-old students and things like that, okay? And so we can just use words right now, and we can say, well, in our classroom, it's mostly 19, 20-year-olds. We've got some 18-year-olds. We've got some people who are older than 21, 22. We have a 17-year-old, and we might have a few people who are older than that, but pretty much almost everyone's somewhere between 18 and 22-ish or something, right? And that works for describing the distribution of data, okay? But perhaps we want a more efficient way to describe the numbers, okay? And perhaps we want a more uniform way to describe numbers, right? So for example, you can imagine going to a different room, right? So we could imagine going to the DMV, okay? I don't know when the last time you had to go to the DMV was, and you have to it's kind of crazy. You have to stand in a line first to even get into the building, and then once you're inside the building, you have to sit in this waiting area and whatnot, right? And then in that waiting area, there's a whole bunch of people. And how would you describe the distribution of ages in that waiting room? Nobody? Okay. It's all over the place, right? Okay. You've got teenagers who are taking their driver's exam behind the wheel test. You've got people who are renewing their driver's licenses and registrations and stuff. A lot of those people are parents, so they've brought their little children along, okay? You've got seniors and whatnot. And so the ages are all over the place, okay? At the same time, we can use words to describe it, right? We can say things like, there really isn't anyone over 100 years old at the DMV waiting room, right? So, as far as the numbers we see, we're not going to see values much bigger than 100, okay? And we're not going to see any values smaller than 0, okay? And as far as the values between 0 and 100, probably most are somewhere between, I don't know, 16 and 60. That's still a huge range, okay? And I don't know, there might be certain concentrations that are some numbers have higher concentrations than others, right? And so can we come up with some better way to describe things than just me, I don't know, giving this vague description of numbers, okay? And that's what today's lecture is all about, okay? How do we describe the values that we see in the data and try to be specific and useful and helpful and clear and concise, but just give people an idea of what kind of numbers you might see, right? And so, so there's a few ways to do this. One is we can do it graphically, and the other is numerically, okay? And this covers chapters 2 and 3 in the textbook, and we'll see how much I'm able to cover in our time here. Some of it you're gonna probably have to read up a little bit in the textbook. Okay, so the values in our data, how are they distributed on the number line, right? Okay, and so just kind of using vague words, we can say something like, most people in the classroom are about 19 to 20 years old. Some are older. Some are younger, et cetera, right? And so this is just kind of fairly vague. I'm not sure what that sound was, but okay. And so we want to do a better job. All right, so if we're dealing with this, one graphic tool, okay, a graphic tool for, we're going to just start with numeric data, and that's probably what we'll have time for today. And I might have to just force you to read the textbook regarding the categorical data. Okay, so for numeric data, something like age, we have the dot plot. Okay, and for the dot plot, basically, each observation is represented by a dot on the number line. It's very simple. Okay, and so we would get something that looks like this, and we would just have our number line 17, 18, 19, 20, 21, 22, 23, 24, okay? And then we would put a dot for every person, right? So we'd say, who's 17? And we have one person raise their hand. We say, who's 18? And I don't know how many people are 18, but we're just going to put some dots here, okay? And we ask who's, now I've recognized. I need more space here, right? So. Okay, and then we go, who's 19? And then more people raise their hands, and we get something like this, and who's 20, and okay, so anyway, you guys get the idea, right? All right, and who's 21, and we'll probably get something like this, and who's 22, and 23, I don't know, okay? And maybe there's no one who's 25, and no one who's 26, but maybe we have someone who's 27. I don't know, I'm just making this up, okay? And this is what our dot plot would look like, okay? And when we're done, how many dots will I have up in our dot plot? We would have 130 dots, right? So if I do this for, I would get 130 dots, okay? And now I'm not going to actually count the data or anything like this, but we would have 130 dots, okay? And so that's the dot plot. Okay, simple enough. Any questions on this? All right. Okay, and then the other thing, which is very closely related, is called the histogram. Okay, so let me just make up. All right, so we got 1, 2, 3, 4, 5. Let me just say 1, 5, 1, 2, 3, 4, 5, 6, 7, 8. Just making stuff up here. 1, 2, 3. Okay, so the histogram basically does the same thing as the dot plot, except somebody might say like, oh, all of these dots, they hurt my eyes, and so I don't like looking at them. I would rather have a bar, okay? And that's basically what we do. We just change the dots, and then we just create a bar of a certain height, okay? So, so that's the next graphic tool that we've got. Again, this is also for numeric data. So we'll say a histogram. Okay, and then, and by convention, the bar that represents everyone who's 17 starts at 17 and goes up to, sorry, it's hard for me to talk and write numbers at the same time. Okay, so if we have one person who is 17, we would have a bar of height 1 right here, okay? And then I don't remember how many people, so we would generally have a vertical axis, 0, 1, 2, 3, 4, 5 or something, and were there 5 people who are 18 or something? 6, 7, 8, 9, 10, 11, 12. Okay, and then for 19 people, I don't know what I said. 12 people who are 19? Is that right? Okay, what did I say? How many people are 20? 6? Wait, is that right? Okay, well anyway, so whatever. We just go through and we just kind of create bars for however many people we have. All right, I'm gonna just do dot, 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 and do this, okay? The thing about the histograms is that you can also create bins of ages, right? So for example, well, for our classroom, there's not a huge range of ages, so it probably makes sense to just have each bin represent one person's age or something like that, right? Okay, but if we did something like how much do you weigh, all right? And I'm not gonna, don't worry, I'm not gonna ask anybody how much they weigh, but you know, we're gonna have people who weigh something. There's gonna be people who weigh 100. If we had a scale and we had you stand on it, there's gonna be people who weigh like 130 pounds, and there's going to be someone who weighs 131 pounds and 132 pounds and 133 pounds. There's going to be different weights, right? And if we say, well, how much do you weigh? And we take each of these things, you know, that range of weights can go anywhere from like 90 pounds to 300 pounds or something, and there's probably way too many individual values to keep track of. And so it might make sense to bin them and say, this is how many people who weigh between 100 and 109.9 pounds. And this is how many people who weigh between 110 and 119.9 pounds. And this is the number of people who weigh between 120 and 129.9 and things like that, okay? So, so that's an advantage that histograms offer over dot plots, is that you can create bins, okay? we can make bins of values, okay? And so, for example, if we record weight, we can create a bin or range and say something like, as far as weight goes, frequency or count, we can say 100 to 109.9, 110 to 119.9, 120 to 129.9, etc., etc. Okay, and we can say there's 3 people and 12 people and 18 people, something like that. Okay. And then you would create the corresponding histogram. And okay, you would have a bar that, again, vertical axis, 5, 10, etc. Okay. I'm just making stuff up again. Okay. A height of 3, a height of 12, a height of 18, etc. Okay. Does that kind of make sense? All right. And so this is a graphic way. Remember, the whole idea behind today's lecture is that we want to be able to describe the distribution of data, the distribution of values, either graphically or numerically. And so these are ways to visually display the values that we see in our data set. Okay. And so, so this is called a histogram. If you just want the table without the bars, this thing over here, this is called a frequency table. Okay. And then as far as the frequency table goes, you can also, instead of just leaving them as the counts, you can turn everything into proportions, okay? Which is helpful if you wanted to compare one classroom to another classroom, but the 2 classrooms are of different size, right? So this classroom, there's like 130 of you or something. But if we went to another classroom, there might only be 50 students, okay? And then it's hard to make direct comparisons in terms of the count of students, right? So if we went to like Santa Monica College or something, and we asked, okay, what is the distribution of students there in terms of their ages, okay? It might be similar to ours. It might be different, okay? At a community college like Santa Monica College, there might be more students who are older or whatever, who knows, right? And but if we're doing just direct counts, it might be difficult to understand that difference. Whereas if you are dealing with percentages, maybe that difference is more pronounced. We can say in this classroom, 70% of students are 19 or 20 years old, okay? Whereas at Santa Monica College, only 40% of students are 19 or 20 years old, okay? And that might be an easier thing to compare, okay? So we have the frequency table, and then I'll just write, if we use percentages instead of counts, I've run out of space. I select everything. I don't know what I'm doing. Okay, never mind. Okay, so if we use percentages instead of counts, we'll call this relative frequency. Okay, is that all right? We're all good there? Okay. As far as histograms go, once we start creating histograms, once we start creating dot plots, then we can start talking about the quote shape of our data, okay? To kind of illustrate this, let me just pull up the textbook here. Ready to go. Okay, just because they have so where am I? Okay, so here's some where did these pictures go? I apologize. We can talk about the shapes of our histograms here, okay? And so, so here is a dot plot of ACT scores, okay? So this is, I guess they asked students, what did they score on the ACT? And these are kind of the numbers that we've seen. They just released the UCLA freshman profile, and it's like every year it's astounding. Like I don't know if you call it the numbers that are required, but just the numbers that people get when they come to UCLA. It's impressive. Okay. Anyway, so we can just say, okay, so looking at this particular classroom's ACT scores, we can see that most students scored around 24 and 25, okay? And the higher we go than that, there's fewer there, and going the opposite direction, there's fewer students moving in the lower direction, right? So we only have one student who scored an 18 and one student who scored a 19, only one student who scored a 31. The max is a 32, I believe, right? That's a perfect. And so this is what we've got going on here. And we might say that this distribution is symmetric, okay? And of course, it's not perfectly symmetric. It's not like you can put a mirror down it and get an exact symmetric thing, but we would say that the shape of this distribution overall is symmetric because the right-hand side looks a lot like the left-hand side, okay? Okay. This is what we got, and we would say this is symmetric, okay, as far as the shape goes, because we're talking about, what's in the middle. We say, the right-hand side, and when we talk about the right-hand side, looks like the left-hand side. All right, what does it mean to talk about the right-hand side? What kind of values do we see on the right? Okay, bigger numbers, right? So values that are bigger than average, okay? Kind of the frequency of values that are bigger than average is similar to the frequency of numbers that are lower than average, okay? Okay, and so this person who scored a 31 on the ACT is much higher than average. And similarly, as if we go in the opposite direction and we say, well, who scored much lower than average, right? If we say the average is something like 24.5, 31 is what? 6.5 points greater than average. Okay, if we say, okay, well, who's 6.5 points lower than average? So 24.5 minus 6.5 takes us down to 18. And we say, well, we had one person 6.5 points above average. And what do you know? We have one person who's 6.5 points below average. Okay, so if we say this is kind of the middle and the average is about, 24.5, 31 is 6.5 points above average, and we have one person. Okay, and then over here, 18 is 6.5 points below average, and we have one person. Okay, and similarly, and of course these numbers aren't exactly the same, but if we look at, how many people we have, 1.5 points above average and how many people we have 1.5 points below average, we get similar numbers, okay? And we see this kind of similar trend of the farther you go above average, there's fewer people, and the farther you go below average, and I guess it's flipped around for you guys, the farther you go above average, there's fewer people, and the farther you go below average, there's also similarly fewer people, okay? And so that's going to be something that we say is symmetric, okay? So other things that are symmetric will be things like height, okay? As far as kind of our skeletons go, it's mostly symmetric. We've got a lot of people who are average, and the farther you go above average, meaning tall people, really tall people, you're not going to have, you have fewer and fewer people the more extreme you get, okay? And then similarly, if you go in the opposite direction, if you go on the shorter side, you're going to also have a similar phenomenon going on, where the more extreme you go on the shorter side, you're going to have fewer and fewer people, okay? So that's going to be something that's symmetric, right? So other examples will be something like height, or all of these kind of skeletal measures, like you can measure your head circumference or your arm length or whatever, and they're all kind of similar in that regard. Okay. Other things like this is not symmetric, okay? This diagram okay, so this is clearly not symmetric. Okay, this is pro baseball players' salaries. Well, not even just pro baseball; it's MLB. Okay, because technically, even if you play AAA, you're a pro baseball player, but you're not Major League. Okay, so maybe the B is redundant there. Okay, so Major League Baseball salaries. And I don't know what the league minimum is these days. But you have a whole lot of players who are at league minimum or certainly below $1 million per year. Maybe they get a signing bonus and things like that. But you have a lot of players who make less than $1 million per year. I don't think they're complaining that they get to play sports for a living, but their salaries are less than $1 million per year, and that's what we have going on here, okay? But I don't know who the highest, Trout? Is that the Highest salary right now? I don't know. Does anyone know what that is per year?
330 million.
That was like the contract, but not per year. Yeah. Was it a 10-year contract or something? I don't know.
14.
14-year. Okay, so what's 330 divided by 14? Okay, whatever. A big number. Okay, and okay, and this doesn't have the latest data here, but okay, you've got certain players who make a lot of money, and it's like literally like 30 times more than the person down here, right? And so 30 times someone else's salary, that's quite a big discrepancy, right? And you know, as far as their franchise goes, they're probably worth even more to the franchise in terms of like ticket sales and merchandise sales and all of that. But you know, they are very well compensated. Okay, and so we would say something like this is heavily right skewed. Okay, so this is not symmetric. We call this, and the heavily is just my commentary being added. Okay, but we would just say this is be right skewed. Okay, and you know, overall the shape, if I were to just kind of it's hard drawing this curve here, but we have something that looks like this, okay? All right, and so this is right skewed, and what this means is that there are some extreme values on the right. Okay, and the right means, as far as the number line, the right means big, right? Bigger, not smaller. So that we have some extreme values on the right that are just much, much, much larger than the low end, okay? Extreme values on the right, none or very few extreme values on the left. Okay, so that would be right skewed. And I think I have a similar graph for left skewed, which, just find it. Maybe I don't. Okay. All right, so left skewed would be just kind of the opposite. So left skewed would be something that looks like this, all right? Okay, and if you have trouble remembering which side is skewed, just think of this as if you were gonna like skewer a piece of meat or something, okay? Which side would you use? You would use the left-hand side. That's the pointy side, okay? And this is left skewed, and so what does it mean to be left skewed, okay? This means some extreme values on the left, some extreme values that are some values are much smaller than others, right? Okay, so an example of something that's left skewed, I would say would be things on like scores on a relatively easy exam. Okay, so whenever you, not you, but if there's a relatively easy exam, then that means probably most students are scoring 80, 90, close to 100, things like that, right? But as far as extreme values go, you're not going to have anybody really over 100%. Okay, maybe there's some extra credit, but there's going to be a max, right? You get everything correct, and that's going to be the max score, and you're not going to have people getting higher than the max, okay? But, and so you're going to have, so this will be like something like 100, and basically a lot of people getting 80, 90, 100, something like that. But inevitably, even on an easy exam, there might be somebody who never attended class, didn't look at any of the content, and just came into the exam cold and randomly guessed on things and scored something around a 30%, okay? And so the 30% is much, much, much lower than the average, okay? And that's going to count as an extreme value on the left, on the lower end, whereas you don't have the same phenomenon happening on the right end, okay? And so that would be left skewed. Okay, is that good? There's a few other words that you should be familiar with. Okay, unimodal would be like one peak. Bimodal is 2 peaks. And then generally anything more than that we would just say multimodal. It's not wrong to say trimodal or quad modal, I don't know. Okay, so what does that mean? One peak means kind of one range of values is most common. And then 2 peaks would be something like 2 ranges are common, etc. Okay, and so this is unimodal. Even the skewed ones can be unimodal. All right, so this is unimodal also. Just saying one range of values under $1 million is most common. Okay. Over here, unimodal ACT scores around 24, 25 that are most common. Okay, and then bimodal could be what time did you eat at Chipotle? And we might see something like this, and this will be like lunchtime, and this will be like dinner time. Okay, this will be like number of customers at a restaurant during the day based on the hour. Right? Like, I think on Google Maps, let's see. Westwood Village keeps closing restaurants. What's a and In-N-Out's always crazy, but let's see if I click In-N-Out, where is it? Okay, all right, so In-N-Out's almost trimodal because you got people going there at like 11 p.m. Okay, so I mean you can kind of see this. There's a peak here, and then there's a slight lull around 4 o'clock, and then it picks up around 7 and 8 o'clock, and then it picks up again around 11 o'clock midnight. I don't know, let's see. Jersey Mike's, I don't think anybody eats dinner there, right? Yeah, this, well, I guess a few people do. Taco Bell, we're gonna see the peak at midnight here. Oh, okay, no, it's just bimodal, all right. Or is it? No, wait, whoa, Thursdays, what's up with that? Okay. This is what I do for fun. Okay. El Pollo Loco gets no love after lunchtime. Yeah. Okay. Okay, so you have stuff like that, right? Okay, all right, so that's the graphic stuff, and now I've got to cover a bunch of numeric summaries for data, okay, to help us describe the data. So we have ways to summarize the data graphically, and now we have words to describe the shape of the distribution. So if we were talking about this classroom, I would guess we would probably say the ages, we might be able to throw in the word right skewed now, okay? So, because we would say, you know, most students, 19, 20 years old, okay? And again, nobody told me who was the oldest student, but I imagine, okay, as far as the youngest student goes, the youngest student is 17, and that's only like 1 or 2 years, maybe like 2 years below like the quote average or middle, okay? But 2 years above the average or middle, if we say 20 is like the average, 2 or 3 years will take us up to 22 or 23. And I'm fairly confident that the oldest student in the classroom is going to be older than 22 or 23, because just because of different timelines for personal lives and life events and things like that. You know, we have transfer students who come in a little bit older, around 24, 25, things like that. Completely not uncommon. And you might have a 26, 27, 30-year-old student in here. And so as far as the extreme values go, and it's hard to think of a 30-year-old being the extreme value in ages, you know, as far as this classroom goes, the extreme value is on the right-hand side and not on the left. Okay, so now we can use words like the age distribution is right skewed, maybe just slightly right skewed or something like that. Okay, if we want to be able to describe, again, the distribution, we might want to be a little bit more specific using numbers, okay? And so we have numeric summaries. Okay, and these are just numbers that we use to summarize other numbers, right? So if there's 130 of you, there's 130 numbers in my data, and I don't want to have to list out all 130 numbers. I just want to say like the average age is 19.7 or something like that, okay? I just want to say something like that, and so I just want one number to be able to summarize the group, and that's what a numeric summary is. And we often call these numeric summaries a statistic, okay? A numeric summaries, also called statistics. These are just numbers that summarize a sample of data, okay? A sample of data, okay? And I think you guys are familiar with a bunch of numeric summaries already. I'm sure somewhere in middle school or high school you learned about the mean and the median, okay? And those are important, all right? So we have the mean, okay? And we get this by, you know, you add up the numbers and divide by n. Or symbolically, we would say y bar is equal to the sum of y divided by n, okay? So mean y bar is called y bar. And this is the symbol for the mean, symbol for the mean of a sample, or the sample mean. Other textbooks use the letter X. I hope it's not confusing. Or does our textbook use X? I forget. Oh, it uses X. Okay. I will change it to X. To be, it's all the same, okay? But I don't know why. Some books use X and some books use Y, okay? It really doesn't matter. Okay, so we call this X bar. So just to be consistent, we'll have that, all right? And that's what it is. And then we have the median. Maybe before I get into the median, let me just say the mean. So we do this thing where we add up the numbers and we divide by n. And I don't know if any of you ever stopped and said, like, why does that even work? Like, this magic idea, okay? Well, the y is a little bit complicated, but another interpretation is that we can think of this as the balance point. So the mean is equal to the balance point of our data, okay? If I So it says the center as a balancing point, and they just draw this thing, and it's kind of just like, if you take these numbers, and if we have this dot plot, and each of these dots were weights, okay, and you needed to put this thing on a seesaw and have it balanced, the mean is the location where you would put the fulcrum, okay, where the thing would be balanced, right? The balance point of our data. So if you have the numbers, I don't know, all right, and let's say our data is equal to 1, 1, 1, 1, and 1, 2, okay, 1, 1, 1, 5, okay. All right, our mean is what? 1 plus 1 plus 1 plus 5 divided by 4, and we get a 2, right? And so this would be, if I have 3 bricks here and a brick over there, this would be the balance point, okay? So balance is if the fulcrum is at 2, at the mean. Okay. So here's the question. If the numbers in your data were 1, 1, 1, and 5, is 2 the best number to use to describe this data set? So it could be something like maybe there's a family with 4 children, and you ask them, how many times have you broken a bone in your body, right? All right, 3 of the kids say I broke 1 bone, and 1 kid says I broke a bone 5 times, right? So would you feel like the best number to summarize, like, well, what's the average number of broken bones in this family? Does 2 feel like the right answer? Not really. You'd feel like I should probably just say 1, but then I also have to address the kid who broke 5 bones, right? Or broke a bone 5 times, or whatever. I don't know. I'm just making up some silly scenario to fit these numbers that I made up on the spot. So sometimes when your data, how would we describe this data if we had to describe a shape? Right skewed, right? Okay. I mean, it's a very small data set, but we would still say it's right skewed because we got one extreme value on the right. And so when your data is skewed, the mean may or may not be the best number to use, okay? So for example, if we go back to our Major League Baseball salary data, okay, and we say, well, what's the average salary of a baseball player? Technically, in order for this thing to be balanced, and if we add up all the numbers and we divide by how many people we have, the average would be something around 3 million, okay? But would it be fair to say that the average salary of a baseball player is $3 million a year, okay? When by and large, the grand majority make less than $1 million, and we have a few superstars who make 30 million or something like that, okay? And they end up bringing the average to be 3 million, okay? So is it technically correct to say that the mean is 3 million? Yes, that is correct. The mean is around $3 million. But is the typical baseball salary 3 million? No, the typical salary is far below that. And so some people will say, if your data is not symmetric, if it's skewed, the mean may not be the best representation to use, okay? It's still technically correct, okay? You've added the numbers up and you divided by n. It's not that you did the calculation wrong, but for skewed data, the mean may not be the best representation. Okay. But this also depends on your perspective. Okay? If you are the owner of the baseball team, or if you're the front office and you have to figure out, well, how much money do I need to pay my players? Okay? You don't want to say, well, the typical salary is less than $1 million, and so to have a 40-man roster, I really only need $40 million. Okay? That will probably get you into trouble, because then you will not be able to hire any kind of superstar players. And, well, I guess depending on who you are, you know, you may or may not have a successful season, right? So if you needed to think of, like, how much money do I need for payroll regarding the players, it might be better to use the mean, which takes into account these extreme values, okay? Even though your typical player, even though most of the individuals make much less money. Okay, so the mean is one numeric summary, and so the other numeric summary that might address this is the median, okay? And the median is kind of the middle value. Okay, this is half of values are above, half of values are larger than the median. And half of values are smaller. Okay. Finding the median is not too hard to do by hand. You just have to arrange them from least to greatest first, and then you find the middle value, right? Okay. And you guys had to deal with the median earlier, right? Like high school somewhere. Okay. So anyway, this is what we'll go with. Okay. So the mean is the balance point, and the median is the middle value. I think that's fine. Okay. It was bound to happen eventually, okay? That's all right. Just reminds me of those viral videos where the person forgets to put on the parking brake, and then it. All right, anyway, okay. Somebody should retrieve that. Okay, I won't get upset if you get out of your seat to pick up your skateboard there. Okay, so anyway, that's the median. Let's talk about. I'm sorry. So backing up, the mean and the median help us describe kind of where the center or where the middle-ish is. Okay, this idea of typical, what's a central value. So we'll say the mean and median describe kind of the center or what might be considered typical. Okay, so again, describing the distribution of ages in our classroom, we might say something like, the median age is 19 or 20 or something like that, okay? Or the mean is probably something around there as well. If the data is symmetric, the mean will be very similar to the median. Okay? So if you look at this, and if you got symmetric data, the mean is going to be the balance point, and then we also ask, like, where's, 50% is greater and 50% is lower. The mean and median will have very similar values. Maybe they're off by they're slightly different from each other by a tiny bit, but the mean and median will have very similar values. Okay, what about skewed data? So let me just throw this on the screen again. Oops. Oh, it's already there. Great. Okay, so here's some skewed data. Where is the median? Where would you say the median should be? The median is where half of the values are below and half of the values are above. So it's a little bit difficult to eyeball, but the median is probably somewhere around 1 million, maybe a little bit higher than that, okay? Maybe around $1 million, okay? So maybe about half of the players make less than $1 million and half of players make more than $1 million, okay? So this might be the median. So we'll say about 50% make less than 1 million. And about 50% make more. Okay. Where is the mean? In order for this to be balanced in terms of skew or whatever, the mean ends up being higher. Okay, so the mean is around 3 we'll just say 3 million. Okay. And so for skewed data, what we find is that the mean is often pulled in the direction of the skew. So wherever the extreme values are, the mean will often reflect this. It will get kind of pulled in the direction of the skew. Okay? So for skewed data, the mean is, quote, pulled in the direction of the skew. Is that good? And so even without looking at a picture, sometimes by looking at just the numeric summaries, you might be able to start guessing if the data is skewed to the right or skewed to the left, okay? If the mean is significantly smaller than the median, that would be an indication that the data is what? If the mean is significantly smaller than the median. This would have been like a little clicker or the online poll question, but I have to talk to the online poll office and make sure the roster is synced up and everything. So, okay, so if the mean is much smaller than the median, our data would be what? Left skewed, okay? Because the mean is generally pulled in the direction of the skew, and so if it's being pulled to be smaller, then that means we've got probably some extreme values on the left, on the smaller side, which would be the left. The data is left skewed. Okay, is that good? All right, so we can describe the center of a distribution of data. And another important aspect, though, is that we are able to describe the spread. Okay? So we have mean and median to describe center. Okay? And then to describe spread, we have standard deviation, range, and IQR. Okay? All right, and the idea of spread is not too hard, okay? All right, and so imagine going to, so we'll imagine 3 rooms, okay? And the ages in the rooms. Okay, so the first room we'll visit will be a second grade classroom. We'll say second grade classroom on first day of school. Okay. What kind of ages will we see in second grade? Seven, right? Pretty much everybody in this classroom, if they're in second grade, at least in America, the way your grades work is just based on age, okay? If your birthday is on a certain day and they're beyond some cutoff point, okay? You're gonna be around 7 years old on your first day of school, okay? So pretty much everyone is 7. Okay, and as the school year goes on, some kids turn 8 and things like that, okay? Maybe someone is 6, okay? But pretty much everyone is 7. Maybe there's one 6-year-old or a couple 6-year-olds. Maybe there's a couple 8-year-olds. But by and large, almost everyone is 7. Pretty much everyone is 7. Maybe a couple 6 or 8-year-olds. Okay. Let's do this classroom. All right, we already tried describing this classroom. And what kind of ages do we see here? All right, we'll say most people are between, I don't know, 18 to 22, okay? And some are outside that range, right? Okay, and then we'll go back to the DMV room. DMV waiting room. Okay, and then we got all kinds of ages. Anywhere from 0 to 100. Okay, probably most are between, it's really hard to say, 16 to 70? I don't know, okay? It's a much bigger range at the DMV waiting room, right? Okay, and so if we had to describe spread, we would say very little spread. For the second grade classroom. And for the DMV waiting room, we would say lots of spread, or very high spread. And then this classroom, we would say like medium low spread. I don't know what's considered low or high, but it's less than the DMV waiting room, more than the second grade classroom. Okay, and we would say something like medium spread. I don't know, all right? And that's fine, but if we want to be more specific, rather than just using vague terms like a lot or a little, okay, what's a lot, what's a little, we can provide numbers, okay? We can say the spread, the standard deviation of the second grade classroom is 0.3 years of age, something like that, okay? I'm just making that up. And we can say the standard deviation of this classroom is 1.2 years, and the standard deviation of the DMV waiting room is 15.6 years, or something like that, okay? We can provide actual numbers that will quantify the amount of spread, okay? And that's what these things are. The standard deviation, the range, and the IQR, they are just ways for us to quantify or provide a number that describes the spread, rather than us having to say lots of spread, very little spread, okay? And those words are fine. You can say lots of spread and very little spread. But if you want to be more specific in describing your distribution, we can use these summaries, okay? So we can say instead, we can say, I don't know, standard deviation equals 0.3 years. And standard deviation, and I'm just making these up, okay? Maybe I'll say 1.8 years. And standard deviation equals 15.8 years, okay? I don't know, all right? I'm just making these numbers up. Don't get mad at me, please. And this is what we have, all right? So rather than just saying little spread or high spread, we can provide numbers and be specific about exactly how much or how little spread there is. Okay, and so now we'll talk about how we go about calculating the standard deviation, or we'll talk about like maybe the formula, or just what this standard deviation entails. And again, it is important that you learn, or I think there is merit in learning how to find the standard deviation by hand, okay? And I will test you on that. But I don't want you to get lost in just like memorizing the formula or memorizing the steps or something, okay? I want you to keep in mind what it represents, and that is, it's just a numeric way to summarize the spread that we see in our values, okay? So keep in mind the standard deviation is a value that quantifies spread. Okay, so this is the important part, and then yes, we will also get into the calculation. All right, so you can think of, there's another term that goes right along with standard deviation, and this is called the variance. Okay, so we've got, so I'm going to just say the standard deviation is equal to the square root of the variance. Okay, and what we're trying to do is we're trying to summarize how much spread there is in our data. Okay, so one way we can think of spread is we can say, well, where is the middle and how far away are things from the middle? Okay, so if the middle's right here and everybody is huddled near the middle, we're going to say there's very little spread. Okay, on the other hand, if the middle is right here and you've got values that are way above the middle and values that are way below the middle, we're going to say there's a lot more spread. Okay, so in the second grade classroom, the middle is 7, and as far as the ages go in that second grade classroom, almost everyone is 7, and so everyone's like huddled right at that middle age of 7. Maybe there's a 6 and maybe there's an 8, but even those are very close to that middle value. Okay, in this classroom, if we say the middle age is 20, okay, we've got some people who are higher and some people who are lower, but even then they're only different from it by a few years. Okay, and then if we go to the DMV waiting room, I don't know what the middle is, 40, and then we say some people are way above 40 and some people are way below 40. We've got something like that. And so what we can say is we can just talk about how much things deviate from the center. Okay, so what's the difference or what's the deviation from that middle value? And when we talk about the variance and the standard deviation, okay, some of the deviations will be positive and some of the deviations will be negative. Okay, so some people are below the average, I guess for you it's this way, and some people are above the average, and so we're going to have positive and negative deviations. And there's a few ways to address this, okay, because if you add up all the positive deviations and all the negative deviations, a lot of times they cancel each other out and you end up getting like 0 deviation total, which is not what we want. Okay, and so the way the variance addresses this is we take the deviations and we square them, because when we square a number, whether it's positive or negative, it's always going to end up positive. And so so that's where we're going to end up. Okay, so we get the variance. So the standard deviation is the square root of the variance, and the variance is going to be what we can think of as the average squared deviation. Okay, and I put average in quotes because we don't divide by n, but we divide by a different number. It's complicated, but this is what we have. Okay, the symbol for standard deviation is S, and the symbol for variance is S squared. It's not V. S squared, to kind of, I guess, emphasize that the standard deviation is the square root of the variance. All right, and so let's take a look here. Okay, so let's just pretend there are 2 families. Okay, and we'll say both families have 5 kids, and the mean age, or the average age, is 9. Okay, All right. And so the question is, do these families, do their lives look similar? Okay. Well, the important aspect that we're missing is the standard deviation. Okay. All right. And so let's say, I'm just making up some names here. We have the Baker family. Okay. And their ages are 1, 5, 9, 13, and 17. All right, and then we'll say we have the Cook family. So the kitchen profession families, okay. And their ages are, we'll say 7, 8, 9, 10, and 11, okay. Both families have 5 children, and both families, the mean age is 9, okay. Those statements are all true. But does life at the Baker family look anything like life at the Cook family? Probably not, right? Okay? Because at the Baker family, you got someone who's preparing to go to college or already going to college, and at the same time, somebody who's in diapers and everyone in between. You have an adolescent and someone, you know, whatever, right? Someone who's watching Sesame Street. Okay? But at the Cook family, the range of ages is a lot smaller, right? 7, 8, 9, 10, 11. They're all born about a year apart, you know, something like that, right? So if we just looking at the numbers, which family has the larger standard deviation? The Baker family, right? There's more spread, they're gonna have a larger standard deviation. Okay, well, let's go ahead and calculate the standard deviation for the Baker family. And we'll talk about if we, I'm gonna go, all right, so, all right, we can see that the Baker family has a larger standard deviation. More spread in ages. Okay. All right, let's go and calculate this out using kind of this definition of variance and standard deviations. The variance we'll say is, we can think of this as the average squared deviation. Okay, and so as far as the Baker family goes, our ages were 1, 5, 9, 13, and 17. And okay, so what is the mean? The mean is equal to 9, okay? And so the deviations from the mean will just be how far are these values from the mean, okay? So we're gonna find the deviations from the mean. Okay, so how far is 1 from 9? Okay, we could just do 1 minus 9, and we would say 1 is 8 years below, okay, and 5 is 4 years below. 9 is right at the mean, so there is no deviation. 13 is 4 years above the mean, and 17 is 8 years above the mean. Okay, so these are the deviations from the mean. And you can see that if I just took these deviations straight and I added them up, they would all cancel out and we would get an average deviation of 0, okay? If I just add these numbers up, because of the negatives and the positives, they would cancel each other out. We would get an average deviation of 0. And so there's a few options. One is to take the absolute value, but for a few reasons that I'm not going to get into, we will square these deviations to make them all positive, okay? So to make everything positive, we square the deviations. Okay? And so if I square negative 8, I get what? 64. Negative 4 squared is 16. 0 squared is 0. Here I get 16, and here I get 64. So these are my squared deviations. And the variance is the average of the squared deviations, okay? Okay, but again, I always put average in quotes because we would take these numbers and add them up, all right? And I would get 160, okay? Except instead of dividing by n, which is 5, I'm going to divide by 1 less than that. So I'm going to divide by 4, okay? So this will be, add them up, and divide by n minus 1, okay? The reason why we do n minus 1 is known as Bessel's correction, and it's to correct for a bias that we induce by using the sample mean rather than the population mean. I don't want to get into it, okay? And it's beyond the scope of this course. If you're really curious, you can come to office hours and I'll explain it, okay? You can also go on Wikipedia and look up Bessel's correction, but it's not important, okay? But anyway, we divide by 4 rather than 5, and so my variance is 40, okay? And technically, the variance is recorded in, because the ages are recorded in years, the variance is technically in square years, okay? Which, I don't know what a square year is, okay? I couldn't tell you. I don't know if there's an interpretation for a square year. It's like, well, I guess there's squared time when you're talking about like acceleration, like meters per second squared and things like that. And I guess, I don't know. Anyway, okay. So variance is recorded in square years, and because people don't like the idea of having squared units, that's why we deal with standard deviations. We take the square root of this thing, will be equal to the square root of 40, and we get something like 6.3246 years. Okay? So this is our standard deviation. So as far as the ages in the Baker family goes, we'd say that the standard deviation is 6.3246. Okay? All right, so an exercise for you to do on your own time is find the standard deviation of ages in the Cook family. Okay, and if you do it, your answer should be 1.5811. Okay, so follow the same kind of steps. Review the notes and see if you can do it without looking at the notes at the exact same time. Okay. Okay, so that's what we've got. We've got the standard deviation there. Is that good? And so anyway, if you go through the math, you say, okay, well, the Cook family, their standard deviation is 1.581. The Baker family, their standard deviation is 6.3246. So this confirms what we already knew, which was that the ages in the Baker family have more spread than the ages in the Cook family. Okay, and so this just reflects what we already know. But that, that was a very contrived and simple example, but it could be useful in comparing like two large classrooms. Okay, you can say, well, this is our intro stats class, and this is the spread of ages that we have, or this is the spread of, or the standard deviation in GPAs, or something like that for this class. And we can go to different departments around campus, and we can say, well, what is the standard deviation of GPAs in this engineering class, and what's the standard deviation of GPAs in this humanities class, and things like that. And we might be able to make comparisons across different departments and say, you know, in this department, a bunch of the grades look like this, and over in this department, the grades look something different, right? And tools, numeric summaries like the standard deviation is helpful in describing that spread. And of course, the visual summaries and things like that, right? You guys go on Bruin Walk and you look at grade distributions and stuff like that. So anyway, that's what we've got there. The standard deviation is especially useful when we use them in conjunction with the mean, and we come up with something called a z-score, okay? And this is helpful because it allows us to identify what we might consider to be an unusual or highly unusual observation, okay? So part of describing a distribution would also be to point out any individuals or observations that might be considered unusual, okay? Part of describing a distribution of data is to point out observations that are unusual, or what we might consider sometimes called outliers. Okay, so what is considered unusual? Okay, so one way to measure how unusual an observation is to use what we call a z-score. There's a few ways to decide if something is weird or not, right? But one way to, I guess, describe or determine how unusual an observation is to use a z-score, okay? And so a z-score is how different an observation is from the mean, but that difference is expressed in standard deviations, okay? Okay, how different an observation is from the mean, but the difference, I don't even need to write but the difference, I'll just say how different an observation is from the mean expressed in standard deviations. Okay. All right, so here's just a silly example. All right, so let's say there's some video game, all right? Some video game, and your friend comes and says, oh, I just started playing this new video game, and I think I'm really good. My high score is 18,000 points. Okay. Okay. Should you be impressed? Now, if you want to be a good friend, you should just say, good job. And support your friend who's proud of their achievement, whether it is truly impressive or not. But internally, you can judge your friend and decide whether 18,000 points is impressive or not. But what information do we need to know to decide whether 18,000 is impressive or not? Well, we would probably want to know what the average score is, right? If the average score is 18,000, then 18,000 is not that impressive. That just means your friend is average. If the average score is above 18,000, okay, assuming higher points are better, okay, then 18,000 is below average, right? And if the average score is, say, 15,000, then you can say, okay, you are 3,000 points above average, right? So first of all, we need to know where kind of the average or where the mean is, okay? So we need to know the mean. Okay, so let's say the mean is equal to 12,000 points. Okay. If the mean is 12,000 points, then your friend's score is 6,000 points above average. And maybe that's impressive. Or maybe it's not, okay? The other aspect we need to know is the spread, okay? Now, if almost all players score between, say, let's say 7,000 and 17,000, okay? And very few players score above 17,000, then we can say, yeah, your score of 18,000 is impressive, okay? And we would need a number to kind of give us this measure of spread, okay? On the other hand, if a lot of players score over 18,000, right? So a lot of players score anywhere from 0 points to like 25,000 points or something, the score of 18,000 is not that impressive. So we need to know, we also need to know the standard deviation. Okay, so the standard deviation, let's say, is 3,000 points. Okay? So, what is our friend's z-score? How different an observation is from the mean expressed in standard deviations? His z-score is what? Okay, so the z-score is, our friend is what? How many points above the mean? 6,000 points above the mean, right? Okay, and how many standard deviations is that? 2 standard deviations, okay? So the z-score is 2, okay? Our friend's score is 2 standard deviations above the mean, okay? And if this is the case, then you can stop judging him or her and say, good job, okay? Because getting 2 standard deviations above the mean puts someone in, you know, around the 97th percentile, okay? Meaning only a small percentage, 2.5% or so, score above that, okay? And so the z-score is a way to kind of measure how different someone's thing is from the mean, but we express it in standard deviation. That kind of standardizes everything, puts everything on the same scale, okay? Whereas someone else could play a different video game and maybe they're also 6,000 points above the mean, but maybe the standard deviation is like 10,000, okay? Then they're not even one full standard deviation above the mean, okay? So the z-score, we kind of the formula for that is x minus the mean, x bar, divided by the standard deviation. It's kind of the distance from the mean divided by the size of the standard deviation. Okay, and this will be what we have. Okay, and our guide is that observations that are more than 2 standard deviations away from the mean, 2 standard deviations or more away from the mean, are considered unusual. Okay, so this is z greater than 2 or z less than -2. Okay, and then observations that are 3 standard deviations or more from the mean are highly unusual. There's something to go along with it called the empirical rule. Also called the 68, 95, 99.7 rule for these numbers. And we say around 68% have z between -1 and +1. Around 95% have z between -2 and +2, and around 99.7, so almost everyone, have z between -3 and 3. Okay, and this applies to unimodal and symmetric data. So things like heights, standardized test scores, and things like that. Okay, so if you have a z between z greater than 2 or less than -2, then that's considered unusual. Only around 5% of the population are that extreme. And then z's above 3 or -3 are highly unusual, as that only about 3 in 1,000 are outside of that range. Okay, I'm going to run out of time here. But the last thing I need to kind of cover is the IQR and the box plot. Okay, so the standard deviation measures spread, okay? And then the IQR, the range and the IQR are other ways to measure spread. The range is the max value minus the minimum value. Okay, and then the IQR, which stands for the interquartile range, is equal to the Q3, or the 75th percentile, minus Q1. 75th percentile minus 25th percentile. Okay. You often see the IQR, or the kind of the middle 50% for kind of things like college admissions. They'll talk about like the middle 50% of SAT scores was, I don't know, whatever it is these days, okay? And that kind of gives you a sense of like what your middle-ish central tendency of scores are, okay? So, you know, be sure to read the textbook on how to kind of calculate these things and find these things. And then they all appear, hang on you guys, in the box plot, okay? And so the box plot is kind of another graphic display and the whole point of the box plot is to basically remove detail, okay? Because sometimes detail can be distracting, okay? So the box plot removes a lot of detail and just kind of gives you a box and a line and maybe a line sticking out of it, okay? And so there's going to be, you know, usually there's some kind of number line, okay? All right, so I don't know, 10, 20, 30, this is not evenly spaced out, okay? But this represents the median, or the 50th percentile. This represents Q3, the 75th percentile. And this is the Q1, the 25th percentile. Okay. You have whiskers. This is called a whisker. Extends to the largest and smallest points that are not considered outliers. Okay. So if you do have an outlier, and just ran out of battery, but if you do have an outlier, it will generally be represented by little circles or dots, okay? And so the whiskers will go to the smallest data point or biggest data point that you have that's not considered an outlier. And if you have data points that are considered outliers, they get represented with dots there, okay? Make sure you do the reading in the book. You'll have a quiz and discussion on Monday, okay? So on Monday you'll have a quiz and discussion. All right, we'll see you guys next week.